up to you. It's up to you.
Yes, could be at any time, and it's not that I have a huge number of slides, so it's all okay.
Okay, it's my great pleasure to introduce worldwide well-known scientist in machine learning optimization, Peter Richtárik. Peter has a big group in KAUST. So he published a lot of papers at top conferences, and now we asked Peter to make a talk at our seminar, all-Russian seminar that was founded by Boris Polyak. And so the direction of research mentioned in this talk, as far as I understand, is about distributed the second-order method. Nowadays, this is very popular direction. And I hope at the end we can ask Peter about the vicinities of this, in my opinion, really very important and modern direction of distributed optimization. Peter, please start.
Thank you very much for the very nice introduction. It's my pleasure to be able to speak in this seminar. This talk is about the paper that you can see at the bottom. So the title is identical to the title of this paper. This is a paper from this year, a few months ago. Let me see whether this works. All right, good. So this is joint work with two wonderful people. Rustem Islamov, who is supposed to be in the audience. Yes, I can see him. So he is a final year bachelor student at MIPT, and this work was done during an internship in my lab. And Shun Kian, who is a postdoc in my team. This is the paper as it looks on arXiv at the moment. I will not really go through all the results. What I decided to do, I want to highlight one of the key results so that everybody understands what is really going on, and then these other derivative extensions and so on, I just leave to you to read if you're interested in the paper. So as you can see, this is from February this year. We also have a poster which was prepared by Rustem. So those of you who don't want to listen to me, you can just talk to Rustem in a few days from now. So this will be presented on Friday at an online workshop dedicated to communication efficient distributed optimization. The poster is online, and if you actually do like and you stay here listening to me, then and you're interested in these topics, you can talk to Rustem and interrogate him and ask him for further details. I'm sure he'll be happy to see many of you there. Good, so here is a brief outline of the talk. I first very quickly describe the problem setup. And then I'll talk about three methods. First, Newton method, then its distributed implementation. So this is just a warm-up. Everybody knows what Newton method is. This will lead to the first new method, Newton star, and then to the second and the main method, Newton learn. And I will not talk about some further variants of this, which we have in the paper, such as Newton learn 2 or cubic Newton learn and so on. So this I will just very briefly outline on a single slide in this section 5. Then I'll talk about some experiments, and I will probably not have time to go to talk about Diana and friends. But on the other hand, you said I have 2 hours, so maybe I'll go there. This is just a few extra slides on some background material. Good, so this is the problem setup. So why we are interested in whatever we are interested in. Here is a brief motivation. It's embarrassingly brief. It's just on one slide. Normally one would dedicate 10 or 15 minutes to something like this, but I was lazy and I'm just doing this on a single slide only. So first of all, distributed optimization and training is important. That's it. So I've just motivated the entire talk. So believe me, and if you don't believe me, then the idea is that if you want to train huge machine learning models with huge number of parameters or many data points, you necessarily have to work in a distributed setup on multiple machines, which may have their own GPUs and CPUs and so on. And in such a setup, the communication between these clients or machine or workers is going to be the bottleneck. And one needs to design distributed methods which can handle this bottleneck. So distributed optimization is increasingly important. Now, almost all of the work on distributed optimization and training is about first order methods. So if you heard of local type methods for federated learning, all kinds of types of SGD and so on and so forth, all of these are first order methods, and they necessarily depend on the condition number of the problem. So tricks such as momentum, acceleration, and so on and so forth, adaptive step sizes, these are all just techniques to reduce the dependence of the problem on the problem conditioning, of the algorithm of the problem conditioning, but the dependence still is there, persists. And the research area is entirely driven in the attempt at reducing this dependence, but the dependence is still there. On the other hand, we have second order methods, which have certain nice properties which the first order methods do not have, such as the Newton's method has a rate, now local, granted, not global unless you globalize it with some tricks. Local speed is independent of any condition number. However, if you want to design a Newton type or a second order type method in a distributed setup, then you would see that all of the methods have one of these two issues. So either the communication cost in each round of communication is just very, very high. And I will illustrate this on the example of a completely naive implementation of Newton's method, because you have to communicate something like Hessians and stuff like this. And this can be very, very, very big amounts of data. Or communication cost is not that high, but then the convergence rate, the theory is really first order like theory, or even worse than first order like theory, which means that the theoretical convergence guarantees do not really show that these are second order methods. So you have rate which depends on the condition number and so on. So the goal of this project is to come up with a method, communication efficient distributed Newton type method, which doesn't have these two deficiencies. So the communication cost in each iteration should be similar to gradient descent. So we don't have to send any Hessians, but we still want to have second order type theory. So we want to have a rate, which would be local in this case, because what we do are some modifications of Newton's method. So the rate will be independent of the condition numbers. That is the goal. And to the best of our knowledge, such methods at the moment don't exist. So here's the problem. It looks a little bit complicated, but it's not really that complicated. So this is just a generalized letter model with regularization. So we try to train a model which is denoted here by X. So X is a vector of the parameters or features which identify the model. And you can see this X appears here in two places. N is the number of machines that we have. So there's not the number of data points, there's the number of machines. So that's why this thing is a distributed optimization setup. And M is the number of training data points on each machine. Now you may wonder, why do we have M and not MI here? This is just for simplicity. So one can do extensions to allowing each node having MI data points, but we just decided to not go there because this just introduces unnecessary extra notation. So we have these AIJ vectors. These are the dimensional vectors, and these are the training data points. So the labels are hidden in these loss functions phi ij, but the examples themselves are AIJs. So AIJ is the example, J the example stored on the ith machine. And then we have an L2 regularizer, which is optional. So lambda could be 0 or could be positive. But for the purposes of this talk, I will assume that lambda is positive for the main result. In the paper, we'll also have a method which can deal with lambda being 0, or actually with any lambda, which is non-negative. This is a slightly different variation on the basic method that we developed here, and I will not describe it. So think of this lambda as something that you don't really need, but because I want to describe just one method and the simplest possible method so that everybody understands it, I assume that this lambda is positive. So these functions are going to be just scalar functions from R to R, and they'll be sufficiently well behaved. So in this case, the second derivatives are Lipschitz. And there's these Lipschitz constants nu for all of them. Okay, so this is the setup. In case there are questions about the setup, please go ahead and ask. I assume this is all fine, and I'll keep going, but please do not hesitate to interrupt me at any point in time. So here's the same problem without all the colors, and I introduced two more pieces of notation. So this entire function I'll call capital F. Now later in the experiments, you'll see instead of F, I use P, because in the paper we actually call it capital P, but for some reason I decided to call it capital F in this talk. And then these functions, which are the averages over the data points stored on machine I, will be called Fi. So this is average of functions Fi plus an L2 regularizer. And sometimes it'd be nice to think of this as just minimization of some capital F function. So that's it. And I introduced this notation because sometimes it'd be nicer to work with capital F, sometimes with lowercase fi, and sometimes with these phi ij loss functions. So that you don't have to actually remember all of this notation, I will introduce this, just keep exactly this slide in the upper right corner of probably half of the slides in this talk. So you don't have to remember. Good, so let's start with Newton. So Newton is a very old method. You can see not every day somebody cites papers from something like 300 years ago. So here is one of the early papers on Newton's method. And one of the reasons why I'm including it here, because you can actually buy a copy on Jonathan Hale bookseller for about $5,000. So if you're interested in original copy, you can actually go and buy it. Good, so that's all I want to say there. Now you can see in the upper right corner, I have the thing that I promised I would. So Newton's method is this method, everybody knows it. You take the current xk and subtract inverted Hessian applied to the gradient. So this is very well known. Now let me rewrite this into the notation of these fi's, so these local functions. So the Hessian capital Fxk is going to be equal to this. Can you see my mouse? The pointer?
Yeah.
Is it?
Yes.
Okay, good. So this is just the Hessian inverted, and this is just the gradient because of how the structure of the problem looks like. Okay, so I'm not doing anything so far, but notice that this is the Hessian that can be computed by machine I, and this other thing is the gradient that can be computed by machine I. So no single machine can perform this Newton iteration because no single machine owns all of the Hessians and all of the gradients. So that's why typically in distributed optimization, distributed training, we introduce a parameter server that acts as a hub for communication among those machines. So in this case, here I illustrated an example with 3 machines. So a machine, the first machine owns function F1, and all of those M examples are hidden there. And there's some initial maybe starting point x0, let's call it xk, we're already at iteration xk, and so on and so forth for all of these 3 machines. And now here is a server, and these machines will communicate through this parameter server. So the first machine computes the Hessian at the current point of the local function and the gradient at the current point of the local function. Second machine does the same, and third machine does the same. So they can do this in parallel, obviously, so not necessarily in serial. So now, once the server has all of these 6 objects, it can actually perform Newton's step, because it can perform this aggregation of the Hessians, which is this orangey thing, and then it can also perform aggregation of the gradients, which is this other color, let's say purplish, light purple, and it can perform Newton's step. Okay, so let's say that this is easy for the server to do. So this could be, let's say, server of Facebook or Google or something like this. So typically the servers could be quite powerful. Once this is done, xk plus 1 is computed and is sent back to the machines, and then every machine now owns xk plus 1, and this process is repeated. So this is a naive, completely naive implementation of Newton's method. So what's the problem with this implementation? Well, the problem is this stuff. Sending D by D matrices, where D could be very large, to the server. So that's the bottleneck. These gradients are not bottleneck. Clearly, this is just RD, but RD by D, this is really a huge amount of communication. So we will not assume in this talk that computation of the Hessian by the machines is difficult. We will simply just compute them exactly. We'll also not assume that it's difficult for the server to compute this Newton step. We assume it's powerful enough, it can do this. So here the bottleneck is the communication channel. And in particular, communicating these Hessians is what is difficult here. Now, if some other bottlenecks exist here, then one would need to go and modify this method appropriately. Good, so that's the main issue with naive distributed implementation of Newton's method. So the bottleneck is communication of these D by D Hessian matrices. And the question is, what can we do about that? Good, so I hope that is clear. So here's a very brief summary of these good and bad things about Newton's method. So Newton's method has one very good thing. It has local quadratic convergence, which is independent of the condition number. So the neighborhood of convergence is dependent on the condition number, but the speed is independent. The rate at which the distances to the optimum decrease is independent of the condition number. So there's a very attractive property, which no first order method can have. On the other hand, you pay by this convergence being only local. But from the point of view of distributed training, this is just a method which is way too expensive because you have to send all these squared matrices from workers to master, and this is just not going to fly. So that's the problem. Now, what can we do about this? So here is the first contribution of this work, which you will all laugh about because this method is utterly useless. So it's useless from practical point of view, but it's super useful from a theoretical point of view and from an idea point of view. So, this kind of a method then allows us to think about what can be done and how to resolve this lack of usefulness issue. So the idea is, we call it Newton star, the method, and star because, not because we think this is a star method, but because we use X star, which is the optimal solution in the method itself. So that is very strange, of course, and utterly useless, as I said. So this is Newton star, and as you can see, we only work with one Hessian at the optimum, which of course you don't have. But bear with me and assume that you have it. So this is a very strange Newton type method where the gradients keep changing, as you can see, but the Hessian never changes. So what is the, first of all, can this even work? Will this have any kind of a rate, or this is just, I'm just imagining things and this maybe cannot work? So there's one question, would it even work if I had this Hessian at the optimum? And second thing, how does this help us in reducing the communication bottleneck of Newton's method, which I described before? So let me rewrite this again in terms of these local functions fi. So just remember that we work with average of n fi's. So this is what we're working with. And now we can assume that this Hessian is actually known by the server. If it's not known by the server, then, well, it can be computed by the workers and sent by the workers to the server, and then that's it. It's sent once, and then the server knows these Hessians and can work with these Hessians. So let's assume for a moment the server knows these Hessians. Well, since the server knows these Hessians, we don't have to send them to the server, right? So obviously we only have to send the gradients, and the server can do these things because it knows all of these things already. It can perform this Newton star type of an iteration, and everything is fine. And then this xk plus 1, which is d-dimensional vector, is broadcast back to the machines, and this process is repeated. So notice that only d-dimensional vectors are sent around, which is exactly what distributed implementation of gradient descent does. But now we're running a second order type method, or at least I'm promising that this is second order type method, even though we're not using any Hessians which change, we only use Hessian at the optimum. Okay, so what's really going on here? So we don't need to, okay, no need, I have way too many O's there, so there should be just one. We don't need to communicate any matrices, or maybe just communicate once at the beginning, and we have the same communication cost in each communication round as gradient descent. So this is all good. Of course, it's useless because we don't know the Hessian at the optimum. So this is a new method. And again, method is a little bit of a strong word because you cannot implement it, but it's a new theoretical method and we analyzed it in the paper. And fortunately, this method has, and maybe a little bit surprisingly, it was surprising to us. And I would like to know if anybody actually can find reference for something like this. I have not seen this before. It seems to be a very simple idea, but I do not know whether this was done somewhere else. So it has a local quadratic convergence rate, similar to Newton's method. So the rate is not, the neighborhood of convergence is not exactly the same, but you have local quadratic convergence rate. So what do we have here? Why is it quadratic? Because we have norm on the left-hand side, and we have norm squared on the right-hand side. So this is why it will be quadratic in the end. X star is the optimal solution. Mu star is just a lower bound on the smallest eigenvalue of this Hessian at the optimum. And by the way, this could be 0. We allow for mu star to be 0. So it's all okay. So if these functions are just convex, this is already satisfied. But in that case, we need lambda to be positive. So either lambda is positive or mu star is positive, but both don't have to be positive necessarily. Lambda is a regularizer. So again, could be 0 or positive. Nu is this constant of Lipschitz continuity of the second derivative of the loss functions. And AIJs are these training data vectors. So this is the result with all the constants. I'm not hiding any O notation anywhere. So this seems nice. So we have a method which has local quadratic rate, which is different than Newton's method. So that seems promising. And if we knew the Hessian at the optimum, we'd be able to implement it very efficiently. So cost of one communication round exactly as gradient descent. So that sounds all good, but of course we don't have the Hessian. So what to do about this? So we have local quadratic convergence rate independent of the condition number. That's beautiful. We have cheap OD worker master communication, but of course we don't know the Hessian at the optimum, so this is useless. But this gives us an idea, and the idea is the following. Well, Newton's method is not the only method which has this local quadratic rate, because you could also use this Newton star. So this suggests that maybe Newton's method is robust to the choice of the Hessian. Okay, this is something that maybe Bfgs and quasi-Newton methods try to exploit, but here is a different point of view. So you could change the Hessian, replace the Hessian in standard Newton's method, which is Hessian at xk to Hessian at the optimum, and still you get local quadratic convergence rate. So this means that maybe there are not just these two choices, maybe there's many other choices which also lead to fast rate. Maybe not local quadratic, but maybe some other type of a very fast local rate, which is not achievable by any first order method. So this is really the importance of this realization. Plus, it also gives us a recipe for maybe what should we be doing. We should be learning the Hessian at the optimum somehow. Okay, so and that's the main idea here. Newton learn. Let's learn this Hessian at the optimum. So we don't have it. How can we learn it on the fly through some learning technique? So here I will stop before I go to this part, and in case there are any questions, I'd like to answer them now.
Okay, so I have a question. Peter, could you please elaborate about the intuition behind this Hessian at the optimum? So you say that it's similar to the so-called SGD star or something like that, or
so I didn't say it, but you know that it is similar. At least I didn't say it today in the talk, but you're right.
So could you are there any connection between these two methods? And
well, there is a philosophical connection. So SGD star is this method which we co-developed with you. So it's a method which is an SGD method, but empowered by the knowledge of the gradients of these local functions fi at the optimum. So how can you possibly enhance SGD if you actually knew this thing that you cannot know, which are the gradients of these fi functions at the optimum? And it turns out that if you had this information, you can automatically make any SGD type method into variance reduced SGD method, and you have no need for any variance reduction mechanisms such as VRG and so on and so forth. So somehow you get a linear rate automatically, and not sublinear rate, let's say in the strongly convex case and so on. So here the intuition is similar. So somehow information at the optimum could help you do well. But here it doesn't help you do better than Newton's method. It doesn't improve the rate. It's still a local quadratic. But here, what it helps you with is just the realization that Hessian is not the only thing that makes the method locally quadratically convergent. That you can have Hessian of the SK, but Hessian at the optimum. So somehow you don't damage the method by doing this.
Yeah.
This points to the robustness, and maybe this points to the direction that maybe we can come up with some learning technique for learning this Hessian. And if and it doesn't have to be the Hessian at the optimum, or the current Hessian could be something in between, okay? And maybe the method will still be fast. So that's roughly the connection.
So am I right that because of this local convergence, since we are close to the optimum in some sense, then Newton method turned out to be robust in changing this. So the motivation was that you can change the gradient by something, or you can change the Hessian by something which is close.
Which is close. Yes, but I'm not. Yeah.
Okay, so yeah, now I see the intuition.
Yeah, it's just close, but the result would probably not hold if you just assume that you have maybe some distance between the true Hessian and some matrix or something like that. Then the local quadratic rate would most probably actually not hold. Mm-hmm. So it's not enough for this to be just close in some sense. We don't have such a result on the paper, but I don't think that would be the case. So somehow not everything flies that is close, but there has to be, but clearly there's more space than just the Hessian at the current iterative X scale.
Okay, thank you.
Are there some more questions by anyone? So I actually don't see the chat for some reason.
There is no question in chat.
Okay, I opened the chat just in case. Okay, so I really want to wait a little bit because I think it's a good idea for people to ask whatever they want before I move to the second part.
Is it crucial to have this generalized linear model structure for this method to come?
So no. So we didn't know that at the time of writing the paper, but now we know, and we're writing another paper. But you'll have to bear with me, and I assume, as in the paper, that we have these generalized linear models. So we didn't know how to handle that differently before, or maybe this was the first idea that we got, but something else can be done also without the structure.
Okay. There is a question in the chat by Konstantin Mishchenko. So do you see it?
Yeah, I can see it.
Okay.
I don't know. We didn't investigate this. So we only thought about the cubic method when we try to globalize what we're doing, but we're not actually designing a cubic Newton star method. So I'm not quite sure. I would rather want to say that probably not, at least from the point of view of whatever the motivation for Newton star was, because this global rate will not be independent of the condition number, so we'll not get the second order like property if second order like property is a rate independent of the condition number. But we didn't really investigate this. Okay, so maybe one more question, then I move on.
Sorry, I have a question that when we are calculating the inverse of Hessian to the gradient, we usually solve a linear equation.
Yes, yes.
Yeah, but in this case, we want to use. I mean, we just calculate the Hessian once. So, is it better to we just calculate the inverse of this Hessian? I assume that we know.
So this method is completely theoretical. So I wouldn't ask such practical questions because I don't want to use this method. I don't know the Hessian at the optimum. So asking such a thing is not going to help us in removing the issue that we actually don't know the Hessian at the optimum. But of course, whenever you solve this Newton system for Newton method, then you're not inverting a matrix, you're really solving a system, try to hot start it and so on and so forth, and use all kinds of maybe iterative techniques for this. We're completely abstracting from all of these issues. We just assume that we can solve this Newton system at the server exactly, and we leave issues such as let's do it approximately to future research, because that's not the heart of the research that we're doing here. The heart is we want to develop a fundamentally new stochastic second order type method which resolves certain open problems in the literature, and these kinds of practicality issues just have to wait in some sense, because we don't even know. I mean, at the moment, imagine we're developing the method together right now in this talk. So at the moment, I'm not going to ask such questions if I don't even know what the underlying method should be. How can I even get a method which has local rate independent of the condition number and the same communication cost as grade in the sense? I need to first get that and get a clean version of it before I can try to make it more practical by asking questions such as how to approximately solve the Newton system. Can I not compute the full Hessian, but do something else, and so on and so forth?
All right. Yeah, thank you about that.
Okay, good. So I guess I'll keep going.
Can I have a question?
Of course, there could be more questions, obviously.
That if you are using the Hessian at iterates xk, you will end up with iterates xk that converge to optimum. The same thing that if you are using the Hessian at optimum, you will get another sequence of xk that converges to optimum. Can you somehow interpolate between these two things? That, for example, can you somehow maybe you average between Hessian at iterate and Hessian at optimum to get different sequence of xk?
Yes, probably, because you could use convexity of the norm and just bound things that way. So probably this would work. But again, this Newton star method is impractical. So building on it by using the iterates formed by this method is not going to fly because we cannot run it.
Yes,
sure. What you suggest probably would work.
Yes, I'm just trying to get some intuition. How can one interpolate through it?
Yeah. So the interpolation that I have in mind is going to be different. So not this type of interpolation. It is going to be some sort of learning mechanism.
Okay, thank you.
Okay. So good. So let's move on. Right. So now the idea is to remove this deficiency of Newton star somehow. So in order to get an idea how we can do that, let's first write down formula for the Hessian of this big function f, capital F, that we want to minimize. So this is the structure of the Hessian. And if you want to just see why, just look at the function here and take the second derivative, and you'll see that that's what you get. And in particular, it has this structure that there are these second derivatives of the loss functions evaluated at these inner products. Now, from now on, we'll assume that these loss functions are convex. So in fact, these second derivatives are non-negative. And then we have these rank 1 matrices formed from the training vectors. So in some sense, the Hessian is just multiple of identity plus a conic combination of rank 1 matrices. Okay, so that's what the Hessian looks like at every single x. Now, let's, in the light of this, let's look again for one more second at Newton and Newton star. So here's Newton star. How do they differ? They differ just in this Hessian. One is at xk, one is an x star. Now let's write down the formulas for these Hessians. And this is how they differ. So both of these are true Hessians of function f at some point. One is at xk, the other one at x star. But we could maybe abstract from this and replace just this shaded region on the right-hand side in the definition, in the formula for these Hessians. So maybe what if we build a sequence of approximations of the Hessian, which is always a conic combination of these rank 1 matrices plus lambda ID. But the coefficients defining this conic combination are not second derivatives of the loss function at x star or at xk, but it's just something else. Okay, so that's the idea. So this is just repetition of the issues of Newton and Newton star. Okay, so that's the idea. And again, by introducing Newton star, we have solved one problem, which is the expensive OD square communication, but we introduce a new problem. So finally, Newton learn looks like this. You keep the gradient here. So this we're not going to be changing, but we change the Hessian. And the Hessian would be some matrix, which we desire out of it. This should be some sort of communication efficient approximation of the Hessian. And we will enforce structure into this HK matrix. So it will also be a conic combination of these rank 1 matrices, but we allow for these coefficients forming the conic combination, these HIKs, to be anything non-negative, and we'll figure out an algorithm how these coefficients should be changing. So we'll not be using second derivative of these loss functions either at xk or x star. We'll just come up with an algorithm for changing these blue vectors or blue coefficients HIK. So Newton learn is exactly this method plus a recipe for how to evolve these blue vectors. So once I describe to you the recipe how to change these HIJs from k to k plus 1, then you know what Newton learn method looks like. Okay, so what do we want out of these coefficients? Well, one thing that we want, what we learned from Newton learn, is that we want them to converge to these second derivatives of the loss functions at this inner product, at the optimum. If this actually happened, then we would be running eventually asymptotically Newton star. Okay, so there's something that we would want. Another thing that we would want, we want the differences between HI and k plus 1 and HIK vectors. So now look at HI and this column here. This is just all of the coefficients put together into one m-dimensional vector on a node I, on machine I. So m is the number of examples on each machine. So this is just the vector of all coefficients on machine I. And this is the difference between two subsequent vectors at iteration k plus 1. And imagine that if this difference actually was sparse, even maximally sparse, so that all the elements of the difference is 0 and only one out of these m elements is non-zero, then in fact it would be very easy to communicate H to the master, because all that we need to communicate is just one of these differences. All the other differences would be 0, and then we need to maybe communicate one of these vectors Hij, which is OD, and we have something which is very, very cheap to communicate. So this is on our wish list. Of course, how to do that at the moment is not clear. And then we also want, ideally out of this method, that it will have a local rate, which if it's not quadratic, then at least it should be independent of condition numbers so that we can see there is a separation between this type of a method and any kind of a first order method, because first order methods will necessarily depend on the condition number. So this is what we want to do. And again, I'll pause here for a minute before I describe how these blue vectors hi are evolved in the Newton line.
So I have a question. Do we assume that, so on the previous slide, you showed that the communication complexity is O of D squared. So do we assume that M, so as far as I understand, server can store, if it's powerful server, it can store, for example, all these vectors aij's, and we just need to send to the server the second derivatives of aij's. So we need to send, for example, in some setups, it is possible to send O of M numbers.
So this is slightly less naive implementation of Newton in case M is not too big. We actually describe it in the paper as a step in between this naive implementation of Newton and Newton star, but I didn't mention it here in the talk. So what you say is completely correct. So if this bothers you, then assume for the moment that M is very, very big. Just imagine M is like D squared, let's say. Just imagine that that is the case. But you're absolutely right. If M is small and we can send all the data aij to the master, then but we're not allowed for some reason to send these functions so that the master cannot do these second derivatives. If for some reason that is not allowed, then and M is small, then there is a much better implementation of distributed implementation of Newton. So if this bothers you, then assume M is very big.
Yeah, okay. Thank you.
Okay. So any more questions, or should I move on and describe now the learning mechanism behind these ages? I'm looking at chat. There's nothing in the chat, so I'll just continue. Okay, so here's the learning mechanism. And this is the entire formula. So what's going on? So first of all, this HIK is the vector of all these coefficients owned by a machine I. So this is m-dimensional vector, as many as examples, at iteration k. And we add to it something. There's some step size times some operator applied to something. And then there's some plus operation at the end. Okay, so this is just the definition of these vectors, hi colon k. And we want this average to be roughly maybe the Hessian of fi at xk or at the optimum or something like that. The CIK is a compression operator. It works from m-dimensional space to m-dimensional space because these are m-dimensional vectors. And we assume it's unbiased, and this should be H. So sorry, typo, I forgot to change this to H. And the second moment is bounded in this way. So this is a common assumption in the literature on compression operators for first order methods. And the best example of this, and I don't have a slide for this, would be the one that to keep in mind is a sparsifier. Rand R sparsifier, and in fact, imagine Rand 1 sparsifier. So this would mean that you take this vector as an input, this difference between the true second derivatives, vector of second derivatives, and the previous estimate of it. And this is m-dimensional vector, and you zero everything out except for one entry, which you multiply by m in order to make this unbiased. Okay, so if you do that, if you use the random 1 sparsifier, then in fact, whatever you're adding to this HIK vector is super sparse. You're only changing one coordinate of this vector at a time. Okay, so you can even think of this as some sort of strange type of coordinate descent method. So you only change one coordinate of it, which means you only change, you only have to send this compressed difference. This blue vector is owned by the master, and the master can just add this multiplier times this compressed difference to it, and it can maintain these blue vectors in that fashion. So we're compressing the update, and this compression of these differences is motivated by a first order method called Diana, and some of the inventors of the method are in the audience. So hello. Good. So so that's the idea here, and this eta is a step size, and in this case, the best kind of a step size is just 1 over omega plus 1 over omega is this variance parameter coming from the compression. So for instance, if m is really big and you use rand1 sparsifier, then this omega will be roughly equal to m. Okay, so the step size will be inversely proportional to that. All right, so this is the idea, and this plus operation is just a projection onto non-negative orthant, because we want all of these coefficients to be always non-negative because of something in the proof. So somehow we would want this to be always conic combination of those rank 1 matrices and not just any linear combination. So once we compute this, we take max with zeros. Okay, so this thing combined with this previous slide, that's the complete description of the Newton-Learn method. So I want to stop here because before I go into any theory, because I want to make sure that everybody understands this method. Otherwise, continuing wouldn't make much sense. So either we lost connection or everybody's thinking about questions.
There is no question. There are no questions in chat, as far as I see.
Okay, but I will insist. This is something that I do. I put people on the spot and I insist on questions. I apologize, but I will insist because I think this is a perfect place to pause for at least 1 or 2 questions.
I guess the devil into the details, and the most interesting thing happens further when we understand what is the rate of convergence, because it's yes, it's how to say, it's, the idea is very nice, but we should understand how compression slow down the convergence, because it's, I guess, the most interesting thing. Okay, let us continue.
Okay, so I'll continue, and if anybody has some questions about this method, this slide or the previous, please really ask, and I'm very happy to go back to it. So again, the method is completely described by this iteration, where you don't replace the gradient, but you replace the Hessian. And you always maintain the Hessian estimate as a conic combination of these rank 1 matrices, and you update these coefficients defining the conic combination using a certain formula which enforces efficient communication through sparsification. So somehow by design, we make sure that only few of these coefficients change, which means only a little bit of information needs to be transferred. So we did it by design. Now the question is what happens with the rate. So this is what happens with the rate.
So So
Okay.
I'm sorry. I have a question.
Apologize. Yeah.
So as far as I understand, you need to have this projection onto non-negative orthon. So, and I'm trying to understand whether the server needs to store all these HIKs.
Yeah, so we're assuming that the server stores all of these HIK, and that's it. So let's assume that. So the server, so at the moment, we're happy to assume anything about the power of the servers and the workers. Okay, we assume they can do whatever they want, and we just solely focus on the communication as a bottleneck. So yes, one way to think of this is that the servers need to know these HI vectors. Now we also have some other variants of this in the paper, which I don't go through, and some of these don't necessarily have this issue, but for the moment, assume that this is actually happening, that we need to store all of these HI vectors.
Okay.
So this is something that shouldn't be a problem at the moment.
Yeah.
Okay.
Also, we have another question in the chat by Konstantin.
Yeah.
And he asks, wouldn't the max operation break unbiasedness?
Yeah, of course it does. So, but one can think of this as a kind of a prox step. So you take something like an SGD step. This is something like SGD step, and then you have a projection. So it doesn't damage anything in the end. So it's okay. All right. So here's the rate. So the rate looks very simple. So it's 1 minus minimum of step size divided by 2 and 5/8. And the step size is simply 1 over omega plus 1, which means the rate is constant or depending on omega and nothing else. So it doesn't depend on the conditioning of the problem at all. So if back to Edward's question, if M is very huge, well, maybe then this omega will be very big if you want to use very dramatic sparsification. But it will be independent of the conditioning of the problem. I can see I copied the same issue here. So this is supposed to be H. So this is a linear rate, clearly. So we're losing the quadratic rate here. But the rate is independent of the condition number, and that's a great thing.
Sorry, could you remind what is capital phi?
So I will do that now. Yeah. So that's the next thing that I want to do. So this is some sort of a Lyapunov function which I will just define. Okay. So something which is nice, something which is meaningful will go down to 0. Of course, all of this is local. So this is local rate. I will mention this at the end of the slide. And this is the Lyapunov function. So it's a combination of distance squared to the minimum and summation with some factor of all of these differences between these coefficients that we learn and the true second derivatives at the optimum. Okay, so for the Newton star method, all of this double sum is just 0 because these coefficients are always exactly equal to this. I can hear some discussion there.
Sorry,
that's not aimed at me. It's not aimed at me.
Okay, Milodžica, do you have a question? I suppose, okay. Just forgot somebody forgot to.
All right, so this Lyapunov function contains the usual suspect, which is distance of xk to x star. But at the same time, the linear convergence of the Lyapunov function also suggests that these coefficients actually converge to the second derivatives at the optimum, which means we actually learn the Hessian at the optimum, provably. So this learning mechanism works, and you can think of it as some sort of a alternative to, let's say, what quasi-Newton methods try to do, even though until recently this was not provable. But this is not the quasi-Newton method. It's just different type of a second order method which learns the Hessian. Okay, so this is what converges. Now, what are these other constants here? So this constant capital R is just the maximum norm of these training vectors. Nu, which I'm not highlighting, this is just the Lipschitz constant of the second derivative of these loss functions. And this is one of the desired property that we wanted to have. We wanted these coefficients to converge to these guys. Sk converges to infinity. And in fact, this theorem says that's happening. So we do probably learn the Hessian. So this mechanism works. And all of this is local rate. We're not going to suddenly resolve the issue that Newton method without any globalization strategy converges locally only, and somehow miraculously this is not going to converge locally only. It does converge locally only, and this is the neighborhood. There's one more assumption that we need, which I'm not actually writing down for this theorem to hold, something about the choice of these initial coefficients, but you can find the detail in the paper. But this is almost precisely the theorem up to that one detail. Okay, so I think I'll pause here again because this is the main result. And all the other results, I'm not actually going to cover in detail. I will just explain them very, very briefly on a single slide.
Sorry, kappa, sorry, not kappa, eta depends on omega. And the question is, what is the typical range for omega for some compression operators?
Right, so for us, the most interesting compression operators are sparsifiers. And the omega will grow with the number of zeros that you want to introduce into the vector. So if you use a random R sparsifier, okay, then this omega will be something like d divided by R minus 1. Mm-hmm. So if you use random 1 sparsifier, so which means you really sparsify everything except for one entry, then omega will be d minus 1. So omega plus 1 will be d. And this is just 1 over, sorry, by d I mean m, which is the number of, because this is all working on n-dimensional vectors. So the most drastic sparsifier will introduce step size 1 over m, where m is the number of data points on each machine.
Yeah, I see. Yes, it's reasonable. It's very natural. Yes, thank you. Very natural result. Yes. Okay. And if you use many components, so say R components, this was eta equals R over m. Yes, for about R over m.
Yes, exactly.
Okay.
Yeah,
very,
exactly.
Thank you.
Yeah. Right. Okay. Is there a question there? Do we gain from using compression? Yeah. So this is.
Can I ask?
I don't know who is asking.
Yeah, it's Yura Malitsky.
Okay. Hi, Yura.
Okay. Suppose we don't use any compression.
Right.
We just want to learn a Hessian. In this case, right. Omega is 0, right?
So what will happen is that the step size, so omega is in general is d over r minus 1, so it'd be 0 in this case.
Mm-hmm. And in this case, rate will be just linear with 1 over 2.
Yes, this would be local linear rate independent of condition number, and it's not local quadratic rate.
Yeah, and this result is also new, I suppose, right?
Yeah,
I never seen this.
Nothing like this existed. So the closest work is about non-distributed analysis of stochastic Newton method by Dmitry Kovalov, Konstantin Mishenko, and myself, but this is not a distributed method.
Yeah, okay, yeah, thanks.
But of course, in that case, this method would just simply turn into Newton's method, and then you should get local quadratic rate. So, and one can actually write this theorem in such a way, I'm pretty sure, even though we didn't try, so that you actually do recover the local quadratic rate of Newton's method.
Yeah, makes sense. Yeah, thanks.
Okay, so now Konstantin's question. Yeah, so we do gain from compression. Exactly is right what you say, that the number of iteration goes up because we lose the local quadratic rate and we get local linear rate. So we make the rate worse, but we gain from compression. And the question is, what is the combined effect? Does the increase in the number of communication rounds going to be too much of an increase or fine increase when compared to the gains we get from compression? So that's exactly the same issue that you have, let's say, when you work with gradient descent and compressed versions of gradient descent. When you compress, you introduce stochasticity, you increase the number of communication rounds, but in each communication round, you communicate less. And the question is there a benefit? And there is a benefit here, and I will show that through experiments. Okay, so that's the main result, and I only had this one goal of explaining this one result, which is the cleanest result we have in the paper, and then all the other more elaborate results and so on you can read on in the paper. I'll just explain very briefly on the single slide. So these are all the results that we have in the paper. I described these two. So I described this Newton star and this local quadratic rate, which is independent of the condition number. So this is theorem 2.1 in the paper. And for Newton learn, this is actually a method which we call NL1, Newton learn 1, first version of Newton learn in the paper. I only described this first result, which is this local linear rate independent of the condition number for the Lyapunov function. But in fact, we have a second result where the distances, so this R is distance, the distances converge at the local superlinear rate. So that's a stronger result for the distances, and is also independent of the condition number. So that I'm not describing here in detail. I didn't talk about the Max Newton method, which you can think of as some sort of alternative to Newton star. In fact, this was the first method that we developed when we started doing this research. It also has local quadratic rate. And I didn't talk about Newton learn 2, the second variant. And the point of the second variant is that this also handles the non-regularized case. So somehow it's a little bit more complicated, but it handles both the lambda positive and lambda 0 case. So that's really the main point. And you recover essentially the same result. It's also local linear rate and superlinear rate independent of condition number. It's just a little bit more complicated. And once you understand the first version of Newton learn, it would be easy to then go and understand the second version. So I'm saving time and I'm not explaining how that works. And then we also wanted to globalize this, and the way we've done it was through cubic regularization, which is due to Nesterov and Polyak in terms of analysis from 2006, and Griwang in terms of the algorithm from 4 decades ago. And this method, for this, we have essentially 4 results. We have a global sublinear rate, we have a global linear rate, but they are not independent of condition number. So obviously, so this is something that you don't have for global rates. But then we also have local linear and superlinear rates, just like before, which are independent of the condition number. Okay, so that's what we have in the paper, and now some experimentation. So we work with mostly regularized logistic regression, and all of these experiments are simulated, which is to say we didn't implement this on n workers in a distributed scenario, but that also means that the plots are actually truthful because we're not showing the time, we're showing implementation independent results, which actually sheds more insight into what's going on. And mostly we use these libsvm datasets with different number of n's and features and so on and so forth. So this is for illustrative purposes only. In one of these experiments, in the final one, we compare against what to us seems to be the state-of-the-art second-order distributed method, which is called bingo. by Crane and Rusta from NeurIPS from a couple of years ago. And in this paper, they compare against all kinds of other second order distributed methods, such as, I believe, Giant, Dane, Disco, and so on. And they say that their method is the best. So we only compare against Dingo because of that. So Dingo has a linear rate. The rate is not independent of the condition number. So this is some sort of a gradient descent type rate, but it has fast communication. Okay, so let's first look at the Newton-Learn, both of these versions. You can ignore the second version since I didn't describe it. And let's look first at the effect of compression, which is in fact what Konstantin was asking about. I can see there's some question there.
Nikita Yudin asked a question. Do we have RK alpha, alpha greater 1 for local superlinear rate, or it is enough to have
Yeah, so what we have is RK, so the ratio between the new distance and the previous distance goes down linearly. So that's what we actually have. So there's a constant, so that's what happens. The ratio of new distance, previous distance goes down linearly. I don't know whether this answers your question, but I hope it does.
Yeah, this is a superlinear rate, but not quadratic, as far as I understand. But superlinear.
Yes.
Okay.
Okay. So the first thing is just let's not compare against any baselines. Let's just look at the method and throw few sparsifications operators at it and see what happens if you increase the sparsification level or decrease the sparsification level. So we've done a bunch of experiments with various regularization parameters. The smaller lambda is the more ill-conditioned the whole thing becomes. And in order not to stare at many of these plots, let's just pick one of them and make it big. So this R is the sparsification level. So remember, we're doing rand R sparsification, which in this case means R1 means we sparsify everything is 0 except for one entry. So we only need to communicate one coefficient by each node needs to, each machine needs to communicate one coefficient and one example, d-dimensional example vector. And you can see that as you increase this, decrease the sparsification level, you go from 1 to 3, the method gets worse. So the number of communicated bits actually increases. And we have seen this even with larger numbers. So because of this, we actually choose in all experiments the most dramatic sparsification level. That seems to be the best. So it's not true that it's better to actually not sparsify. It's exactly the opposite. We should sparsify maximally. And we can ignore all of these other, this is for the Newton-Learn 2, which I didn't describe, and there's another parameter P there, and you can ignore that. So just look at these two plots, this one with the star and this one with these blobs. And this would continue increasing as far as I remember, as you increase R. Okay, so that's the first lesson that we learned. Now let's compare against Newton, which is essentially the extreme case of this, where you don't sparsify anything. So again, we've done a bunch of experiments. Let's look at one plot. So here you can see that Newton needs to communicate 2 to the power of 31 bits in total from the workers to the master in order to push the residual to machine precision. And Newton-Learn 1 with this extreme sparsification only needs 2 to the power 25 bits. So there is many orders of magnitude difference in terms of communication efficiency between Newton-Learn and Newton. So this really, I suggest that this is a good idea and that this is not just a theoretical result, but in fact, there is some merit to it and the difference could be really, really huge. So we are very pleasantly surprised that there's such a big difference. Typically, when you improve on some methods, maybe it's some percentage or something like this, but this is many orders of magnitude. Good, so now let's compare against Bfgs. Again, we've done a bunch of experiments and I'm picking one semi-randomly chosen experiment and we see similar situation as when we compare to Newton-Learn. So initially, these things are quite comparable, as you can see initially. So it all depends how far you want to go to X star. But if you want to go really far, then Newton learned with the most drastic sparsification is again many orders of magnitude. This is like what, 3 orders of magnitude or whatever this is, or 4 better than Bfgs implementation. So we can now compare against first order method Diana, an accelerated version of it, which reduces the dependence on the condition number in the same way as Nestor of acceleration does for standard gradient descent. So accelerated Diana can be thought of communication. It's something like Nestorov's method distributed, but with communication compression. That's one way to think of this. And done in the right way. So again, we've done a bunch of experiments. I'm picking one random one. And what we can see is again, the same kind of a picture when you compare against accelerated Diana with different compressors. So this is random dithering, random sparsification, natural compression, different compression mechanisms. All of these are worse than the most dramatic version of Newton learn. On the other hand, it has to be said that Newton learn 2 in this case, thus similarly to A Diana with natural compression, worse a little bit than A Diana with random dithering, but better than A Diana with random sparsification. On the other hand, we didn't play with some other compressors for Newton learn here. Okay, so finally, let's compare.
I'm sorry,
yeah.
May I ask a question? So yes. As far as I understand, R in A Diana is d/4, which is d is dimensional, yes?
Yeah.
So
yes, that's correct. So there's no Hessians, one compresses the gradients, yeah.
Yeah, okay. So have you compared against, so why did you choose d/4, not just 1 to have?
So I don't know how to answer this question, but Rustem maybe has an answer. Rustem is here. Can you answer this question?
So the reason actually was because we compared with different, of course, R, but actually, let's say, if we choose R is very small, close to 1, something like this, the performance of Diana with random sparsification is much worse than if we choose something like d/4. So this is the reason.
Okay, so it somehow optimized R for A Diana, or?
Yes, somehow for a Diana with random sparsification, we do not have such results like for Newton learn. Then the less is R, the less R is, the better in terms of communication performance. So okay. That's why we have chosen such R.
Okay, thank you for the clarification.
All right, thank you, Rustem. And finally, we compare against the second order method, which to our understanding is the current state-of-the-art method. So again, I'm picking one of these plots, and you could see the same picture, that there is many orders of magnitude difference in the number of communicated bits between Dingo and Newton learn. So this is all very encouraging, and to us, this means that maybe this is a good direction to go in, and one can try to make this method better in many various ways. One can be creative about in what ways, and we're already doing some of these improvements, but it will really take the entire community or community of people who are interested in this to really push this further, because I believe we're essentially at the beginning of the journey of how second order methods could we make communication efficient in a distributed fashion. So this is kind of the end, and I only have 3 slides on Diana and her friends, so to speak. So this is just some background things. I'll go through this very briefly. And the reason why I'm doing this is because Diana was the mechanism for which we applied to learn these coefficients. And those of you who don't know what Diana is, and even those those of you who know what Diana is, maybe this kind of an overview of these works will be useful to you. So this method is somehow a method which kind of started this research. So Sega method can be seen as some sort of a single node Diana algorithm. This is the original Diana paper from a couple of years ago, which is all of these are first order methods. So this is some sort of an improved Diana method where we removed some constraints that we had in the Diana paper. So for instance, in the original Diana paper was only analyzed with a very particular ternary quantization operator. And this generalized Diana uses any unbiased compressor, just like we have used here, and also introduces some other tricks such as variance reduction within each node. There is a general theory by Edward and Philip and myself of many SGD methods. We were in a single theorem. You also analyze variance reduced methods, including Diana. So this is further development. We managed to also generate something like the Diana method for fixed point problems. So then we managed to accelerate Diana. There is another unification with Jidze for non-convex functions, which also includes non-convex analysis of Diana. Diana can be used to improve the best rates for error compensation, which is the way of handling biased compressors. You can work with Eduard, Dmitry Kovalyov, and Dmitry Makarenko. One can also do Diana on a network, on a graph. So there's a decentralized Diana, and this is currently the best results for decentralized method with communication compression in the strongly convex setup. One can further improve Diana and accelerate Diana with matrix smoothness. So this is a very recent result. And finally, very recent result also by Eduard, Konstantin Bulachenko, Jidze, and myself. This is a Marina. So there's a different name from Diana, but it's inspired by Diana in some sense, and also by Page algorithm. So here we compress also differences, but true gradient differences. This is a bias estimator, unlike Diana, which is unbiased, but it achieves the current theoretical state-of-the-art rate in the non-convex setup for distributed communication efficient optimization. So that's a very brief overview. And in fact, this is overview which should be chronological. So somehow these papers developed roughly in this order. Thank you very much.
Thank you for a very nice talk. Please, questions? I guess you may, how to say, use microphone and ask questions directly without chat. Okay, let's wait a couple of seconds.
May I ask a question meanwhile?
Yeah.
Peter,
yes.
when you learn weights Hij,
yes,
I didn't understand why it works, but to me it looks like SGD update.
Yes, that's correct.
So I don't know in the analysis how heavily you based on that, but when I see SGD,
yeah,
my naive question would be, why not to do variance reduction for that update?
I can explain. So so you don't need variance reduction. So this indeed is something like one step of projected SGD, but in each iteration, you have a different problem that you want to solve. Because this XK changes, this is always just one step of projected SGD applied always to different quadratic optimization problem with the regularizer. So we don't write about this. This is something, this is true also for Diana method, but we didn't write it in the paper because we didn't know it at the time. But you don't need variance reduction because this is actually the full gradient. Okay, and for some reason you don't need it. You will not benefit from variance reduction. This is something like one node compressed gradient descent with the full gradient information. So this has a linear rate automatically, and the linear rate is exactly the rate given by the step size. So it's 1 minus 1 over omega plus 1 to the power of k. 1 minus step size to the power of k. So there's no need for variance reduction because it already has a linear rate. So somehow that kind of a one-step recursion is used in the analysis at one place.
Yeah, thanks.
Let me look at the chat. Is there something there? No.
So did you have some toy experiments when you can actually compute the Hessian and the optimum? And did you compare against this against the best methods? Yeah, against Newton star. Yeah.
So there's a question for Rustem. I don't know whether he has done that.
Yeah, we compared, and so honestly, this Newton star has really good performance. So it is really close to standard Newton. So that's why I think that is not so correct to compare Newton Lone with Newton star, because Newton star is much faster. So it has the same number of iterations that we need to converge, something like 6, 5, and so on, like Newton, standard Newton. But for example, Newton Lone, so we need something like 100 iterates.
Yeah. Okay. Thank you.
Yes, thank you very much. Very nice talk, and very, very popular direction, in my opinion. I guess it's just started, and I hope to see a lot of papers in this direction, because maybe direct application to machine learning, and this is a generalized linear model. This is a very specific class of problem formulation where we have linear model and non-linear envelope, and I guess this direction is much wider, and we may expect some new results in a recent.
Thank you very much for the nice words. So we did manage to remove this assumption of generalized linear models, but this is ongoing work which will only be released next month. So that is not essential, and we look at a few other things. Of course, it's too soon for us to say exactly what we're doing there, but we certainly do think that this is promising direction. And there's just many things which we believe could be done here. Yeah, and it's not possible for us to do all of that, and we'll be very happy if other people joined us in this endeavor.
Thank you very much for your talk, for the direction you choose. I guess this is very useful for us. Okay.
Thank you.
Thank you. Next Wednesday we will have a conference, and announce will be sent later. Thank you one more time, and see you next Wednesday.
Thank you all. Take care. Bye-bye.
Bye-bye.
Thank you for the talk. Goodbye.
Bye.